and hopefully you can all see it.
We got it. Thank
Assuming
you.
you'll tell me. Okay, great, good. Excellent. Well, it's a pleasure to be here and to give this talk to you all and to get your thoughts and questions toward the end. I will note a slight modification in my title. You note that I took out load models from the title that Jack gave you. And the reason was just because as I was putting the slides together, I realized I had a little bit more that I wanted to, that I had time to say. And so we're focusing just on fast timescale dynamics and transmission line models in particular. So this is work that's joint with a number of my current and former students. Gabrielle Colin-Reyes and Ruth Kravis have done the bulk of the heavy lifting on the research results toward the end, and Rodrigo Henriquez and Jose Daniel Lara, who are now at NREL, have done the bulk of the heavy lifting on the dynamic simulation models that we use to do our research. And I want to acknowledge the support from the UNIFI Consortium, specifically the Solar Energy Technologies Office at DOE. And some of this work was prior supported by the Advanced Grid Modeling Program and Ali Ghassamanian's program at DOE. Okay, so timescale coupling complicates dynamic simulation. So some of you may have seen this type of slide before. But this is the figure here. The y-axis doesn't actually mean anything. It just gives us an ability to order some of the different kinds of phenomena that you might model in a power system. And the x-axis is showing you the sort of inherent timescale of the given phenomena. And for many decades, phasor domain simulations have been used to study these slower timescale dynamics. Some would call it Newtonian mechanics of rotor angle dynamics, also potentially some voltage dynamics. But if one were thinking about very large scale area studies and interactions between different machines, that was generally considered to be enough to do a phasor domain simulation and ignore the faster timescale dynamics like stator transients, switching surges, and lightning propagations. For those types of things, EMT simulations are typically used for these faster timescale dynamics. And the interesting thing about our emerging world grid, in which we have many more inverter-based resources, is that inverter-based controls often live in this very fast timescale range. And so then that tends to couple together the things that we have typically thought about when we care about large-scale device interaction studies, tends to couple those dynamics with the faster dynamics that we've often tended to ignore and only use EMT simulations for. So when we think about our choices that we're faced for doing dynamic simulations, we're beginning to grapple with orders of magnitude more state variables. So what we're looking at on the x-axis here is the number of equations that you might write down to do a dynamic simulation. Here in, back in the day, 5-10 years ago, we were thinking about synchronous machine dominated systems. One might have hundreds, thousands of equations to write down in a large area study. But then as we move up to an inverter dominated systems with many more inverter based resources, we get increasing numbers of equations, but then we also get a phenomenon of increasing stiffness, meaning the ratio of the fastest to the slowest dynamics. And what happens in that case is that we go from a simulation world in which explicit numerical methods will suffice to one in which implicit numerical methods are required to do the solving. And if you're not familiar with numerical integration tools or haven't studied them for a while, the big difference that happens when we go to implicit numerical methods is that essentially each time step requires at least one root finding effort. That is, there's some iteration that happens within a time step to find the roots to a system of equations. And so implicit numerical methods tend to be slower for obvious reasons, but they're required when you have a very stiff system. So we think about existing simulation tools, commercial tools, they don't typically accurately capture the fast dynamics and or they don't easily scale. So if we think about accuracy, a phasor domain simulation, which ignores those fastest dynamics, it is typically unable to accurately capture, model network dynamics or other electromagnetic scale phenomena. And then if you think about solution time, an EMT simulation could capture all of those dynamic phenomena, but because EMT simulators work with very, very small time steps, a 30-second EMT simulation just at the island of Maui could take many, many hours to run, even on a large machine. I think somebody might be unmuted in the background. Perhaps you could check your mic if you're unmuted. I will note that there are some tools, for example, DigSilent is one in this case that can simulate portions of a network as an electromagnetic transient simulation. And so then you could think about sort of pruning off part of a network, doing EMT simulation there, and then integrating that with a larger, much faster to simulate phasor domain style simulation. It's still hard to do system level interaction study in this case. And so then, sort of setting all of this up, what we see is a critical need for new tools that can accurately and quickly model and simulate these complex systems. And in this case, one of the central questions that I'll be addressing in the talk is in what conditions do we need to model the very fastest timescale dynamics? So this, if you think about this question about phasor domain versus EMT, which I'm actually going to try to enrich to beyond just those two possibilities. One way that you can answer that question of whether or not we should be using an EMT simulator is if we know whether or not the fastest timescale dynamic will really matter for the kinds of conclusions that we're going to make in the studies that we're interested in doing. So this is one of the questions that I hope I'll at least begin to answer by the end of the talk. But I'll also try to help you also understand some alternatives to simply sticking in this EMT versus phasor domain simulation. So specifically then what I'll be doing, the talk comes in two rough parts. The first is just to introduce a power system simulation software package that's been developed partly in my group at Berkeley called powersimulationdynamics.jl. And I'll motivate that and explain why I think it's something that some of you may be interested in working with. And then the second part, I'll be investigating some of these more empirical research questions, investigating the need for fast dynamics. And so we'll ask questions like, what drives changes in small signal stability conclusions when you ignore fast dynamics? That is, what if a small signal stability conclusion changes, if you include versus ignore fast dynamics, what's driving that change? What is it that we need to be aware of? And this is just an example of an eigenvalue plot that I'll explain in more detail later. And then the second sub-question of this second part will be a deeper dive into thinking about how many line states you need to simulate in order to get fast and accurate dynamic simulations. If you think specifically about an EMT solver, one of the most important things that distinguishes it from the capabilities of a phasor domain simulator is that it's got the capability of modeling transmission line dynamics. The phasor domain, we've just got algebraic transmission lines, versus in a EMT solver, you can capture the full wave propagation dynamics of a transmission line. And so I'll show you some work where we've tried to investigate some of these issues within our own powersimulationdynamics.jl. Okay, so let me get back to this part. I hinted at this a couple of slides ago where I was suggesting that when you're considering the spectrum of tools that one could use for power system simulations, one doesn't need to simply confine themselves to a phasor domain versus an EMT simulator. Those, of course, are the main things that are available commercially. But there's a very wide range of other types of simulations that one could do. If you think about a phasor domain or a quasi-static phasor simulation or a positive sequence simulation in the extreme, there's an important approximation that's getting made in that case, where effectively what's happening is that you're averaging out dynamics on your 60 or 50 hertz cycle. So the quasi-static phasor simulation, then when you think about something like PSSE or PSLF, we're typically sitting over here in phasor domain sequence, positive sequence, where, as I suggested before, you're ignoring network dynamics. You're modeling the network just as an algebraic power flow solve. And the dynamics are effectively just wiping away. You're having to wipe away the fastest timescale dynamics in order to do that. If you think over on the other extreme of power systems time domain simulation, you're running electromagnetic transients. What most people think about is EMT, which is a point-on wave or waveform simulation. And in that case, you could, with inverters, you could either ignore or include the switching models of the transistors themselves on board the inverter. But then you can see, okay, we've got a whole lot of other things that sit in here for different kinds of simulations that one might consider doing. And the one that I'm going to be, the types that I'll be focusing on today are DQ0 simulations. So if you study DQ transformations, DQ, very importantly, is not an approximation. It's just a mathematical transformation from an ABC coordinate frame. So you're taking a point-on wave mathematical representation and representing it in this DQ formulation without any approximations. It's just a mathematical transformation. Now, the thing that we will do, the way PSID is set up, is that we do DQ, just DQ rather than DQ0, meaning that we don't model any potential phase imbalance. And that would be a future work thing to be. But I'm going to try to explain or motivate a little bit more about why living in DQ, we think, presents potential advantages for simulation. So when you're in DQ, because you've just done a transformation rather than an approximation of the system dynamics, then we can still capture as much of the fast time scales as we wish, just as you could in another electromagnetic transient simulation. But then you'll see over here, this is actually another model form that I'll work with later, where you could run DQ simulations with an algebraic network, which comes close to capturing the style of simulation that you do with positive sequence, but without having to make all of the same approximations that you do when you do positive sequence. Okay, so this enabling software that I've mentioned a couple of times before, Power Simulation Dynamics.jl, or PSID, is a Julia-based software package that grew out of the SIP, or Scalable Integrated Infrastructure Planning project at NREL. And it was further developed at Berkeley, specifically Jose Daniel Lara and Rodrigo Henriquez, who were my PhD students that also contributed to the NREL project. This is a fully open source simulation tool that enables modeling, and the way we like to frame it is that it enables modeling and simulation innovation. So it's constructed in a balanced DQ formulation. This enables electromagnetic fidelity, but also it's structured, it's set up, and we won't go into these details today, to enable rapid prototyping of new converter models and develop of large-scale testing of state-of-the-art numerical integration methods. And I'll show you some results on that. For those of you who may be aware of the Julia programming language, it's a tremendously powerful tool that it can be used as a scripting language, something like Python, but has the computational speed and power of something like C, which is often the sort of gold standard for scientific computing. It supports what we call surrogate integration, which means, in this case, surrogates would mean scientific machine learning surrogates, where you're taking a portion of your network and potentially replacing it with a machine learning model. I won't go into that today, although we have done some of that work in the past. And it's open source. There's actually thousands of installs that we've had since the software was launched, and we've got contributors on 3 continents. And so just examples of some recent outputs just on the simulation side. There's a large library of power system test cases for computational experiments, including the 240 bus WEC model. It's integrated with MIT's differential equations.jl libraries, and I'll show you some examples of how we leverage that integration. And it implements a range of speed up features such as automatic differentiation. So let's talk just a little bit more before I start talking about numerical integration, its accuracy. So we've done a tremendous amount of benchmarking of PSID against commercial tools like PSSE, which is a phasor domain simulation tool, and PSCAD, which is an EMT simulation tool. And here's just some examples of validation where we're reporting the root mean squared error between PSID simulations and either a phasor domain simulation, which is in the top set of, or the top table, or an EMT simulation in PSCAD, which is in the bottom table. You can simply see that we're getting very low root mean squared errors across these, between these commercial solvers and what we're using for PSID. Gives us a little bit of confidence that the tool is operating correctly. But then if we think about, and I think somebody still is got their mic on, so I can hear some background noise. To be great if you could mute yourself. Okay, so you can see two things in this simulation on the left. So the first is just a comparison of the time domain traces of PSID, which is this Julia software tool that we've developed, versus PSCAD, which is EMT, versus PSID, which is a phasor domain simulation. And so, and then the simulation is just for, I forget in this case, I think we're looking at a simple 3-bus network, and we're looking at the voltage of one of those buses, and there's a generator trip that we simulate. And what you can see is that the dynamics from PSID and the EMT PSCAD simulator lay immediately directly on top of each other. And then PSID, this set up as in quasi-static phasor, which essentially means that we ignore the line dynamics. You can see that sitting beneath that, there's something that looks like the average behavior, and that's just this is the time average in one way, is how you can think about it, of what's happening in the faster electromagnetic timescales. So you can see again, just to the traces, we've got some accuracy. But what's, I think, particularly interesting is that the simulation, the solve, happens for PSID much faster than it does for PSCAD. And so in this case, we've got adaptive time stepping that captures the fast dynamics and maintains a significantly faster solution time than PSCAD. So specifically what we've got is this, for the total PSCAD run for this simulation that we did, it was something like 1.5 minutes, or about 135 seconds, or sorry, 95 seconds in this case. And then you can see comparisons to PSID with different solvers, FBDF versus IDA. And these are just two different implicit numerical integration solvers. So you can see that we're working with orders of magnitude, an order of magnitude or faster simulation time. Okay, so let me talk a little bit more about what I think is interesting then about working with an open source tool like PSID that integrates with other widely available open source numerical integration modeling tools. So this is just showing some benchmarking of the performance of PSID simulation time. In this case, I forget what model we were simulating. I believe it was the IEEE 9-bus model. It might be written here. But you can see that we can, for different amounts of error in the numerical integration solver, the parameter that governs the error that the numerical integration solver strives for in the ODE integration. For different amounts of error, you can see the simulation time that we get across different types of solvers. For a quasi-static phasor case, this is essentially where we're ignoring that algebraic network or ignoring the dynamic network, versus an EMT solver, where we're capturing things like stator fluxes, filter dynamics on the inverters, and the fastest control loops on inverters. The takeaway that I want you to get here isn't so much which numerical integration tool works best, but just that it was very simple for us to simply call different numerical integration solvers in order to test which ones would work best. And so it enables us to, as systems evolve, as we start looking at different types of dynamic phenomena, to continue benchmarking and verifying what is the right solver to be using, rather than being locked into a particular commercial solver. And you can see that in this case, the solver that you would use for the faster time scale, the one that has the lowest simulation time for the quasi-static phasor versus EMT. It varies, it differs based on what type of solution or solve you're trying to do, what type of dynamics you're trying to capture, as well as what types of error you're striving for. So the best solver depends on the application and the type of contingency being studied. Okay, that's PSID. Please let me know if you have any interest in it and working with it. What I'm going to do now is move on and start talking about some of these more empirical questions that I suggested we've been working on, where in this case we are using PSID to answer these questions. But these are questions that are meant to not just be confined to what one would get out of PSID, but more broadly to understand questions like, when do we actually need to model fast dynamics? So to remind you, a phasor domain model couples buses in a simulation via algebraic line models. And those line models ignore the electromagnetic dynamics of the lines. But then also one ignores very fast timescale dynamics like stator magnetic fluxes and the fastest of the inverter states. Whereas an EMT simulator captures all those detailed physics, including transmission line wave propagation, frequency dependence on the transmission line, as well as these other factors like magnetic flux dynamics and so on. And so we're at a point right now in the power system simulation world where as we add more complexity into inverters that have fast dynamic states, the default approach, or the approach that people would take to ensure that they know that they're capturing all the detail they need to do even a large scale area study, is an EMTs. And so then if you need, clearly, if you need to study line dynamics, to study inverter-based resource interactions at high penetrations, then an EMT solver would require a tremendous amount of computing power, especially at large scale. And so then the question that I want to address is, in addition to line dynamics, just the other fast dynamics that one could potentially model in an EMT solver. I want to understand, can we start to distill phenomena or cases in which we absolutely need to model those fastest dynamics, and cases where it could be okay to go ahead and proceed with a large-scale interaction study that ignores those fastest dynamics. And what I'm actually going to do, and this sort of brings us into the UNIFI world of grid-forming inverters, is talk a fair bit about how, excuse me, the type of inverter that you model and the characteristics of that inverter can have very strong impact on your answer. Do I need to model the fast dynamics or not? So there's a little bit of prior work in this space. And there's a lot of different conclusions that have been made. So some prior papers have concluded that line dynamics are very important to model to investigate things like small signal stability in power systems. And then there's some other papers that actually come to the opposite conclusion, that it's not necessary to model line dynamics. And so in what follows, in the remainder of the talk, I'm going to aim to fill some gaps in the literature and see if we can start to bring together some of this diversity of opinion on when you need to model fast dynamics and when you don't, by systematically examining the relationship between inverter parameters and approximations of fast dynamics, as well as studying the importance of increasing levels of line model fidelity. And we'll address these questions in the specific context of increasing inverter-based resource shares, and in particular, thinking about the impact of both grid-forming and grid-following inverters in your simulation exercise. So one of the first things that we did to start this work was we surveyed the literature to try to understand, for both grid-following and grid-forming inverters, what types of parameters different researchers are using to describe the control loops on board those devices. Perhaps it's not a surprise to some of you, but there's just an enormous range of parameters that researchers are using in their studies. And so I won't go through every single parameter here in the table, but I do want to point out the ranges. So these are not exactly the ranges that we found in the literature, but it's roughly the range of parameter values that you see different researchers using for each one of these different types of controller gains or filter inductances, for that matter. And so this brought us to the conclusion that whether or not you're thinking about including fast dynamics in your simulation, and whether or not including those fast dynamics would alter the kinds of conclusions you might make in something like small signal stability or in investigating your transient dynamics, we hypothesized at least that it must depend on what choices you make for the parameters, because there's just such a broad range here and implying very different timescales of control loop application. So the way that we began mechanically just doing this study is we started with a well-known model to many of you. This is the IEEE 9-bus model. And we modified it to place a synchronous machine at bus 1, a grid forming inverter at bus 2, and a grid following inverter at bus 3. We used the Marconi generator model at bus 1 because we can easily remove the stator flux dynamics from that model, just cancel it out. We used a virtual synchronous machine at bus 2 for the grid forming inverter. And then the grid following inverter at bus 3 has the standard PI control loops on real and reactive power on the other loop. And so then we looked at 2 system cases. So this is before we start thinking about varying the parameters. We thought about 2 cases, and we want to understand how, specifically in this case, small signal stability conclusions differ if we simulate either full dynamics, which is in this case including filter dynamics on the inverter, stator flux dynamics on the synchronous machine, and then a dynamic pi model with, in this case, the dynamic pi model would be terminal at the ends of either line, a dynamic line model, that is, dynamic pi line model. At the end of either line, you've got a capacitance and then a series inductance along. I'll talk about even more detailed dynamic transmission line models coming up in just a bit. So we include all of those fast dynamics, and then an algebraic case where we represent those dynamic states above just with algebraic approximation. So then we sampled from that range of parameters that I showed you a couple of slides ago, as well as a number of other parameters like loading on the 9-bus model, line length. We looked at this is a multiplier on the nominal level. So we looked at shorter line lengths versus longer line lengths to try to understand how does line length, if line length impacts whether or not you need to be doing dynamic simulations. And then we also looked at different levels of penetration of inverter-based resources, as well as different shares of production of the inverter-based resources coming from grid-forming inverters. And then, okay, so we sampled from all of those different values that wound up giving us over 12,000 different parameter combinations to then execute a small signal stability simulation for, or simulation of small signal stability evaluation for. And just one more little point here, we did sample those parameters to constrain them to live within a set of calculated speed ratios, where the speed ratios are just governing the gains, the relationships between the gains in voltage and current control loops, as well as outer control loops and current loops for the different types of inverters. So we also made some other just simplifying assumptions to try to keep the space of parameters that we, choices that we studied small. We had grid following and grid forming control loops. The current controllers, we made them identical. And we also made the gains on the grid following P and Q loops identical. Okay, here's our first kind of key result. So what we're looking at on this slide is the size of the largest eigenvalue on the x-axis for the algebraic model, and on the y-axis for the dynamic model. So we've got all of those dynamic states included. And you might look at this and you think, wow, we've got a lot of positive values here, meaning positive real part, meaning an unstable simulation. That may not come as a total surprise because we didn't choose these parameters in a way that tuned them specifically to make the entire state, the entire system stable. But about a third of the parameter combinations that we selected were actually stable. Okay, so then the key takeaway here that I want you to look at is that in many, many cases, the dynamic model has a much larger, largest real part. So this y equals x line, if a dot lines up on this y equals x line, then that would mean that the dynamic model and the algebraic model are identical in terms of the size of the largest, of the real part of the largest eigenvalue. So if you're above this line, what that means is that the dynamic model has a largest real part. The place that I actually want to focus is down here. So a blue dot means that, that the models differ. That is the stability conclusion, stable or unstable, for the dynamic versus the algebraic is different. So right down in here, you can see there's a cluster of green points. That actually means that you have the same conclusion of stable. The orange points are the same conclusion of unstable. And then the blue points is where they differ. The blue points up here, the dynamic model is unstable, whereas this algebraic model is stable. And the points over here, the dynamic model is stable, whereas the algebraic model is unstable. So we see a very large number of cases in which the system is stable according to the dynamic simulation, or sorry, the algebraic simulation, the algebraic model, but we come up here and the dynamic is actually unstable. And so then our question is, what's driving that? Why do we see that there's this large number of cases in which the algebraic model is giving you a stable small signal stability conclusion, whereas the dynamic model is not? And there are a number of different things that cause the eigenvalues or this report of eigenvalue size to be different. But the two that we saw that had the biggest impact had to do with the grid following inverter. So what we see on this first plot is a delta lambda. So this is the difference between the algebraic and the dynamic largest eigenvalue. So a negative value would mean that the dynamic eigenvalue is larger, that is more positive than the algebraic one. And then what we have on this in the x-axis is the outer loop grid following inverter real power gain. And you may have noticed before I said that we also equate it to the proportional gain of the reactive power control loop. So both reactive and real power control loop on the grid following inverter are larger in this case versus a smaller value over here. And so as you increase the gain on that grid following inverter, we see that that's when this sort of difference of opinion opens up. And similarly, over here, this is showing, again, this delta lambda. Again, negative means the dynamic has a larger eigenvalue, tends to be less stable. And then versus the share of inverter-based resources that are coming from grid-forming inverters. So this is actually mirroring the result that we saw with the grid-following inverter proportional gain, which is that as we squeeze out the grid-following inverters and just replace them with grid-forming inverters, that's what's happening as we go from left to right on the x-axis here. Then this difference of opinion between the dynamic and the algebraic models tends to get at least smaller or even fully go away. Okay, so then we started wondering, well, what is the eigenvalue that's moving rightward? We thought one possibility is that there is a mode that is present in the algebraic model that's just getting pushed across, more or less unchanged, except for it gets larger, getting pushed across into the right half plane. Or there's a mode that is only present in the dynamic model that is very sensitive to changes in something like the grid following inverter controller gain. And in fact, it's the second case. So this is showing the imaginary and real part of the eigenvalues from the small signal stability assessment. And I'll just go ahead and zoom right into the inset. So what we're looking at, if it's a green symbol, that is a case with a smaller grid following inverter outer loop gain, and therefore the system is stable. If it's blue, it's got a larger grid following inverter outer loop gain. And either the system is algebraic and stable, or it's dynamic simulation and it's unstable. And so what you can see is that it's this pair, this complex pair of eigenvalues that begin in the stable case that sort of blow past all of the other eigenvalues of the algebraic state and move into the right half plane to destabilize the system as you increase that controller gain parameter. So we did a couple of other just basically sanity checks to make sure that the result we saw is robust. And so in this case, we took exactly the same simulation, all of the same parameter choices, but we replaced the grid following inverter at bus 3 with a grid forming inverter. Yes, that is. And then we, oh, no, I'm sorry, I got mixed up. In this case, we replaced the grid forming inverter at bus 2 with a grid following inverter. And then we keep the grid following inverter also at bus 3. So now we have synchronous machine at bus 1 and grid following inverters at 2 and 3. And the result looks essentially the same. That is, we get a large number of cases in which the algebraic approximation has a stability, stable conclusion. The dynamic approximation or the dynamic simulation, which is higher fidelity, gives you an unstable conclusion. And then we did the reverse. We said, what if we remove the grid following inverter at bus 3 and replace it with the grid forming inverter? And then run all of the parameters all over again. Unsurprisingly, this is really just kind of consistent with everything that we've seen so far. In that case, all of the eigenvalues basically line up on this y equals x line. So removing that grid following inverter brings us to a situation where the algebraic approximations are sufficient for characterizing the small signal stability of the system. Okay, this will be the last little section of the talk where now I'm going to zoom in a little bit further on the role of line dynamics. So I didn't show you this figure before, I probably should have. This is a picture of the so-called dynamic pi model that we used for the last little bit of investigation, where we've got at either terminal of the line, capacitors, and then an inductance along the length of the line. And so it's just in that pi shape. Of course, you may know well about the sort of standard pi model. And this is just the full dynamic representation of that, where we have both ordinary differential equations on both capacitance and inductance on the line. But there's if you think about the telegrapher's equations, you may well know that it's actually a very discretization of a transmission line into a bunch of smaller segments to get you to the point where you could actually think of that as a system of partial differential equations. So there's some studies that Salvatore D'Arco and others did now 10 years ago, originally developed models for DC cables that can be represented in DQ form. So the reason we got interested in this particular form is that we were working with a DQ model, this PSID, and we wanted to be able to represent line dynamics in that case. And so this, from where my mouse is, right here, about a third of the way from the left of the slide, all the way over, that's one model, where the idea is that you could discretize the model in space so that you've got capacitances along the whole length of the transmission line and inductances and resistances sitting in between each pair of capacitors. But then you could also, in order to capture frequency dependence, you can put multiple segments on each branch. And then each segment has got a different inductance, and that enables you to provide frequency dependence, that is, depending on the frequency of the disturbance that's propagating on the line, the way it transmits is going to be different. So the advantage of using this model form is that we can work with it in DQ representation in the extreme of many, many segments and many, many branches. You wind up getting to a system that would look just like a PDE representation of power system transmission line dynamics. And then it facilitates comparison of dynamics eigenvalues just one assumption at a time. So working with the PSID, we can remove multiple branches, for example, or multiple segments and look to see how does that impact, taking away frequency dependence, for example, how does that impact the fidelity of our transmission line modeling. We can do that all within the same framework that we've been working with so far, PSID. And then, but of course, as you might be thinking, the disadvantage is that as you increase the number of branches and the number of segments, you're going to increase the number of states in the simulation time. So we have to sort of manage that as we go through. Okay, so we ran a couple of different simulation cases just to keep things simple at the start. We just did a very simple 2-bus model with a grid forming inverter on one side and a synchronous machine on the other. And we have, because of the way that PSID currently simulates transmission line disturbances, we begin with 2 transmission lines and then just trip one off to have a sudden shift of load flow to the second line. And then we also looked at the 9-bus model. In this case, we investigated 2 different types of line trips. So removing the line between bus 5 and 7, which is the heaviest loaded line in the system, and also removing the line between bus 4 and 5. And so we investigated different scenarios of types of trips of transmission lines, but then also looked at different line lengths, different loading, and as well in the 3-bus model, different locations of grid forming, synchronous machines, and grid following inverters. But our base case was the one that we looked at in the prior study. Okay, so this really just mirrors what we saw in the earlier results for this is small signal characterization. The system eigenvalues for different line models for grid forming versus synchronous machine 2-bus test case follow a pattern that looks like this. So MSMB is multi-segment, multi-branch. So that's many different segments for wave propagation, many different branches for frequency dependence in that. A green dot is multi-segment single branch. The red dot is dynamic pi, and the blue dot is static pi. Because of the way that we had to plot this, we want everything on one plot. Some dots cover up one another. So if there's a blue dot, then we've also got red, green, and purple sitting underneath it. So the static case, those eigenvalues all have their own sort of analog in the dynamic and the MSSB and MSMB. If there's a red dot, then we've also got the green and the purple sitting with it. And then the green and the purple dots is sit up here on their own. So these, if you look at participation factors, unsurprisingly, these eigenvalues in the large red oval are dominated by the line states. If you look at the participation factors, these eigenvalues, which across they're there for all of the models, are dominated by the grid forming inverter and the synchronous machine states. So in this case, our takeaway is that the line state models are far from the imaginary axis. So this is the largest of those. But as you saw in our prior work, adjusting a parameter, for example, the grid following inverter gain, outer loop gain, can push one of those eigenvalues over into the right half plane. This chart is just showing you the difference in the stability boundary. So again, in this case, we're looking at the key thing that I really wanted to understand in this case is, do we get different stability conclusions for that dynamic pi model versus the higher fidelity multi-segment single branch or multi-segment multi-branch models? And so there's not a whole lot to see here in that all of the lines are on top of one another. So this is giving us a stability boundary as a function of how long the lines are in the system versus how heavily loaded it is. And anything down and to the left would be stable, anything up and to the right would be unstable. So for all of these different cases, and because I'm running out of time, I won't go into all of them, what we see is that each one of those different line models, especially the dynamic pi versus the multi-segment single branch, multi-segment multi-branch, are giving us the same stability conclusions. Something that we still need to circle back to and look at is changing those parameters as we did in the prior case, especially that I'm showing you this out of sequence. We did the found that grid following outer loop gain after we had done these simulations. So it's a to-do to come back and look to see, does the multi-segment single branch or multi-branch model yield qualitatively different stability conclusions as you change those gain parameters. But in this case, for these sets of parameters that we looked at, the line models don't influence the small signal results across a wide range of cases. Okay, last little bit, and then we can do a little bit of Q&A. We're trying to think about, okay, how can we start thinking about it a bit more carefully in application and specifically time domain situations in a high inverter-based in-feed situation. So this is just a quote from a NERC report that's a couple years old now, where they concluded that a significant contributor to unreliable performance of inverter-based resources has been just poor commissioning practices, and looking at simulations of things like, in this case, battery energy storage or BESS ride-through performance was not adequately assessed during the interconnection process. So then what, this kind of motivates what we want to do here is to say, well, if we're looking at something like voltage magnitudes, or perhaps it's inverter filter currents, trying to understand saturation effects on the inverter, how much does it matter whether or not we capture the full line dynamics for doing those types of studies? So here's just some example traces. In the top case, this is the 2-bus case, and we're doing that branch trip in the top case. We're looking at a case with a shorter line, 100-kilometer effective line, and then kind of stretching the limits of what might be possible, a very, very long 500-kilometer line on a 2-bus case. And so what we see in this case, what I think is interesting is it's actually, okay, so, and then we're looking at, on the y-axis, filter current on the grid forming inverter in the first column here. And then on the y-axis in the second column of plots, we're looking at the voltage magnitude at the bus that the grid forming inverter is connected to. And then the blue line is the algebraic case, and the red line and green and purple, which are on top of each other so you can't see them, are the dynamic line models. The dynamic pi is the red, and the multi-segment models are purple, and there's a green sitting underneath it. So what we see here is that, well, okay, we're getting some things that are perhaps not surprising. That is some faster dynamics in both voltage or current and voltage that occur that we excite on those dynamic line models versus the algebraic case. But then we're also seeing that some phenomena like a large voltage dip, albeit on a very fast timescale, that comes from the dynamic line model that's not captured in the static pi model, as well as some very large currents that are captured in the dynamic or the static model, which might indicate that you're approaching some sort of an overcurrent situation on inverters and a clipping or a saturation block engaging on the inverter current controller, versus for the dynamic models, those currents aren't as large. As you might imagine, you can construct cases that give you a completely different set of phenomena. That is, perhaps the algebraic case shows lower currents or lower voltages and so on. And so when we started digging into all of this, and I think in the interest of time and to get some Q&A, I'll pass through all of, I've got a few more plots that I can show you. The main conclusion that we wind up seeing here is that it's impossible to rule out the need for including transmission line dynamics if you're interested in things like inverter voltage ride-through or overcurrent saturation, when we're looking at a system in a world with high inverter-based resources delivering power into the system. So I think I'm just going to quickly skim through some of these slides, just do my takeaways. So first, coming back to the PSID part, this should say DQ simulations enable fast simulation of transmission scale device interactions, even with fast time scale dynamics, and enables this middle ground, if you recall that sort of flow chart that I showed you of phasor domain and EMT at the extremes and other stuff in the middle. We're leveraging that middle ground to get faster simulation times with still EMT style fidelity on many of the phenomena in the system. On the small signal stability side, our key takeaway is that including dynamic states is important when you have high grid following inverter penetrations and high outer loop gains on that grid, on those grid following inverters. And then what we see is that does not appear to be that important to include for small signal stability to include dynamic states, these very fast dynamic states with all grid forming inverter synchronous machine systems. And so far, what we see is that the very high fidelity line models, these multi-branch, multi-segment models, don't require, aren't required for doing any of this. It's sufficient to have a dynamic pi model. I think that requires a little bit more investigation. For time domain simulations, what we see is that the simulations can differ quite strongly on very short timescales, depending on the line model. This may not be too surprising. What we were hoping is that we would see perhaps some trends in terms of when we can just fully ignore the fastest of the dynamics. However, what we do see is that the differences usually dissipate very quickly, barring an unstable case, which is what comes out of the first part. So in many cases, what we did see is that the dynamic pi model, and I skipped over this at the end, that its dynamics are actually amplified relative to a multi-segment model, meaning that if you really want to capture the fidelity, the dynamics faithfully, it's important to go all the way to a multi-segment line model versus just do the simple dynamic pi approximation. So our key recommendations then are keep your grid following inverter outer loop proportional gains low and include full multi-segment line dynamics if short timescale dynamics matter for the studies that you're doing, even if you're doing large area interaction studies. Okay, and I think we have at this point a couple of minutes for questions. Thanks for listening.
Duncan, thank you, Duncan. Appreciate that. That was excellent. As I mentioned, please put any questions that